Hello there, welcome back to my channel. In this video, we are diving into an essential concept in complex numbers, the modulus of a complex number. The modulus helps us measure the size or distance of a complex number from the origin in the complex plane. Whether you are solving equations, analyzing geometric interpretations, or working with vectors, understanding the modulus is a key building block. Let us explore what it is, how to calculate it, and why it is so important. Now, given a complex number a plus bi, the modulus is represented by the absolute of z, and this is just the modulus of a plus bi, and this is a squared plus b squared. So this is what the modulus of a complex number is. Now let us use this to solve some examples to better understand the concept. So let us find the modulus of the following. So we have 5 plus 2i, and we also have negative 4 plus 3i. So for the first one, to find the modulus of z, this is going to be 5 plus 2i. In this case, a is your 5, your b is your 2. So you have 5 squared plus 2 squared. And this is square root of 25 plus 4. And this will give a root of 29. You can't simplify this any further, so you just have to leave it as it is. Okay. For the b, we have modulus of z to be equal to the modulus of negative 4 plus 3i. And in this case, we have negative 4 squared plus 3 squared. Note that negative 4 squared is the same as negative 4 multiplying negative 4, which is negative will cancel out negative, so you have positive 16. Don't make the mistake of writing negative 16 instead of positive. So this simplifies to positive 16 plus 9. 16 plus 9 is 25, and square root of 25 is 5. So the modulus over here for b is 5. Let us consider a third question. Let's say we have z to be equal to 1 plus 2i. In that case, our modulus is going to be 1 plus 2i, which is just 1 squared plus 2 squared. We know 1 squared to be 1, 2 squared to be 4, so this is just root 5. So that's how to find the modulus of a complex number. Now we have some question that we have to show that some statements are true. So let us look at this question. We have to show that the modulus of z1 multiplying z2 is indeed equal to the modulus of z1 multiplying the modulus of z2. So as we did in our previous video, we will let z1 be equal to a plus bi, and we let z2 be equal to c plus di. So we have z1 dot z2. This is first of all, let's simplify. Let's find z1 dot z2 first before we find our modulus. So z1 dot z2, this is a plus bi multiplying c plus di, and we have to FOIL it. So first times first, so a multiplying c, we have a c. This multiplying this, we have a di. These two multiplying, we have cbi, and the last two terms multiply, we have bdi squared. And remember, I squared is negative 1, so this changes to minus bd. So the real part is just ac minus bd, and the imaginary part, we are going to have ad plus bc. I hope this helps. So now to find the modulus of z1 dot z2, Note that this is z1 dot z2. We are going to have square root of the first term squared. So we have AC minus BD squared. Then plus the second term, which is AD plus BC squared. Okay, so now let's simplify the right hand side. For the right hand side, we have modulus of z1, and this is going to be the square root of a squared plus b squared. And the modulus of z2, we're going to have c squared plus d squared. So now if we multiply this, if we multiply z1 and z2, we are going to have square root of a squared plus b squared multiplying square root of c squared plus d squared. Note that if, for example, if we have square root of 2 multiplying square root of 3, this is square root of 6, right? You just have to multiply what is inside, what is under the square root. In this case, the same approach over here. All that we have to do is to multiply what is inside the square root. So we have a squared plus b squared multiplying c squared plus d squared. Now, comparing these two, is this the same as this? No. So let us try to simplify this further. In that case, we have AC minus BD squared, which is this. If you are to simplify this, you can, first of all, there's a short procedure to do. You first of all square this because of the squared. So if you square AC, you get a squared c squared. Then you bring this sign, which is negative, so you have negative here. You bring this 2 down. Then you multiply by AC and BD. And the last term is negative BD squared. So negative BD squared is just positive, or negative squared is positive, then B squared D squared. So this is what you're going to get. So let's do the same thing for the second term. So we have AD plus BC or squared. So the same thing, we have this squared. So we have A squared D squared, then plus this. So we have plus, the 2 comes down, we multiply A, D, B, C, then plus B squared, C squared. Now let us combine this. So having AC minus BD squared, then plus AD plus BC squared, we are going to have A squared C squared minus 2. Remember, this is just ABCD, right? So we just have ABCD, then plus B squared D squared. Over here, we have A squared D squared, then plus 2AD, which is just 2ABCD, then plus B squared, then C squared. Notice that these 2 cancels out. So all that we are going to have left is A squared C squared, then plus B squared D squared, plus A squared D squared, then plus B squared C squared. So in this case, we can factorize some terms out. So let's say we factorize A squared out. We are going to have C squared over here left. There's another A squared over here. So if we factorize that one out, we are going to have positive D squared here. Now let's factorize B squared also out. So we have B squared over here. So we have B squared, then we have D squared plus C squared. Now since this and this are the same, we can now add these 2 right here. So we can have A squared plus B squared, then we can also have C squared plus D squared. And now remember, everything is under the square root, so we can now bring the square roots. We have A squared plus B squared and then c squared plus d squared. Clearly, you can see that this is the same thing as this. So you've shown it. Okay. So this was, let's say, the A. For the B, you also to show that you have z1 plus z2 is less than or equal to z1 plus the absolute of z2, which is the modulus, right? So in that case, doing as we did before, we have z1 plus z2. This is just a plus bi plus c plus di. And if we group the reals and the imaginaries, you're going to have a plus c, then plus I over here, b plus d. So in that case, if you find the modulus of z1 plus z2, this is going to be equal to the real part squared, then plus the imaginary part also squared. Okay, now for the right hand side, we have the modulus of z1 to be equal to a squared plus b squared, and the modulus of z2 to be equal to c squared plus d squared. So now if we add the two, we are going to have, so z1 plus z2, we are going to have a squared plus b squared, and the next one we're going to have just plus square root of c squared plus d squared. So how do we know if this is indeed lesser than this? So first of all, let us just pick some random numbers, right? Let's say we have a to be 1, b to be 2, c to be 3, and d is equal to 4. So on the left hand side, we are going to have z1 plus z2, the modulus. We had square root of, now a plus c, we have 1 plus 3 squared. Then b plus d, we have 2 plus 4 all squared. So 1 plus 3 is 4, so 4 squared. And 2 plus 4 is 6, so 6 squared. Now note that 4 squared is 16, and 6 squared is 36. So this simplifies to root of 52. Okay, let us do on the right hand side. On the right hand side, we're going to have a squared, which is 1, b squared, 2 squared, which is 4, plus the square root of, now c squared, 3 squared is 9, d squared, 4 squared is 16. So we have square root of 5 plus square root of 25, which is square root of 5 plus 5. Now, to simplify this, remember root 52 right here is approximately 7.211. Root 5 plus 5 is approximately 7.236. So if you are comparing, clearly you see that 7.211 is less than or equal to 7.236. And if you pick any random number at all, this should work. Okay, now let's look at a different question. We have to express 3 plus 4i over 4 minus 3i in the form a plus bi. Now, given this question, to simplify, right, remember this is division. Then as I said, whenever you have division, all that you have to do is to find the conjugate of the denominator. So now the conjugate of the denominator is 4 plus 3i. Then we have the same thing as over here. So this is just equal to the numerator, then another numerator right here, and we multiply the denominators as well. So we have 4 minus 3i and 4 plus 3i. So we FOIL it again. So we have 3, which is this, is going to multiply the whole of 4 plus 3i. In the second term, this 4i will multiply everything here. So we have 4 plus 3i. Then we divide by, again, we have 4 multiplying everything, 4 plus 3i. Then we have minus 3i multiplying 4 plus 3i. So let's go through it together. 3 by 4, we get 12. 3 by 3, we have 9. 4 by 4, we have 16. And the last two terms, this by this, we have positive 12i squared. So 12i squared just simplifies to negative 12, remember. So in that case, we're just going to have negative 12 here. Now 4 by 4, we have 16. Then plus 12i minus 12i. Then this by this, we have negative 9i squared, which is equal to positive 9. So remember that. So since we have positive 9 over here, we can cancel out some terms. So positive 12 and negative 12 cancels out. Then we have negative 12i and negative 12i will also cancel out. So the only terms that you are going to have left is we have 9i plus 16i, which simplifies to 25i. And in the denominator, you have 16 plus 9, which is 25. So this also cancels out this. So you're just going to have your final answer to be I. So the question said we should write it in the form of a plus bi. So a plus bi is simply the real part being 0. So we have 0 plus I. And that is your answer. Okay, now let us look at our last question. So for our last question, it says that if x plus yi is equal to a minus bi over a plus bi, and now x minus yi is equal to the square root of 1 minus I dividing 1 plus I, we have to show that x squared plus y squared is equal to 1 in both cases. Okay, so let first of all consider the first case where we have x, you have x plus y is equal to a minus bi, a plus bi. Remember, to simplify, you have to find the conjugate, so you multiply by a minus bi. So the conjugate of this is a minus bi, then multiply a minus bi, right? So now if you simplify, you should get a squared minus abi minus abi, then plus b squared I squared. Then you divide by a squared minus abi plus abi minus b squared. Yeah, so minus b squared I squared. So this was just simplified. So now b squared I squared is just minus b squared. So if we are to group the real terms, we're going to have a squared minus b squared. Then if we this and this, if we add the 2, we have minus 2abi. In the denominator, minus b squared I squared simplifies to positive b squared. So we have a squared plus b squared. Then clearly you can see that these two terms cancels out. So we just have this left. So we have x plus yi, right? So we have x plus yi to be equal to, now we can rewrite this as a squared minus b squared out of a squared plus b squared. Then minus the imaginary part, remember there is an I here. Then we have 2ab out of a squared plus b squared. Remember, we can do that because these two terms share a common denominator, this, right? That's why we've been able to divide the expression into two. So now the x over here corresponds to the first term right here. So it means that our x is equal to a squared minus b squared over a squared plus b squared. Now your y corresponds to the coefficient of I here. So in that case, we can have our y, remember there's a negative here. So you have to bring a negative to a squared plus b squared. So the next thing to do is to check if s squared plus y squared is indeed equal to 1. So this is your x. So we have a squared minus b squared over a squared plus b squared all squared, plus you have negative 2ab over a squared plus b squared then all squared. So now let us simplify this to see if we are indeed going to get 1. So for this part, let us simplify this first. So a squared minus b squared all squared simply means writing the term twice. So we have the same thing right here, a squared minus b squared out of a squared plus b squared. So all that we have to do is to multiply the numerators and the denominators. So this by this, you get a exponent 4, then minus a squared b squared, then minus a squared b squared again, then the last two terms will give you b exponent 4. We do that same thing for the denominator. We have a exponent 4, a squared b squared plus a squared b squared, then plus b exponent 4. So now let us see if we are going to get the same thing for okay, let's simplify this first. So the next one is we have minus 2ab squared, so we are writing it twice. So we have another minus 2ab, then a squared plus b squared. So if you multiply these two, this and this, we have positive, remember, positive a squared and b squared. And the denominator just simplifies to what we had over here. So we have a exponent 4 plus a squared b squared plus a squared b squared plus b4. So this thing really takes time, so you really have to pay attention when you are doing it. Now, since we are adding this and this, let us add what we have here. So for the first part, we can simplify further. We have a exponent 4. This minus this is just minus 2a squared b squared. Then we have b exponent 4. Then everything, let's say that everything, okay, let me write it out not to confuse you guys. Let's say we have a squared b squared. A squared b squared, we have it 2 times, right? So we can have plus 2a squared b squared plus b exponent 4. Then we are adding this now, so we have 4a squared b squared over a4 plus 2a squared b squared plus b4. So now since we have a common denominator, we can write one big denominator, right? So we can have a exponent 4 plus 2a squared b squared plus b exponent 4. And all that we have to do is to just add in the numerators, since the denominators are the same. So plus b exponent 4 plus 4a squared b squared. So now we get to see in that on the top we have a exponent 4, which is this, plus b exponent 4. Now this and this, we can add them and we can have plus 2a squared b squared. In the denominator, we have a exponent 4 plus b exponent 4 plus 2a squared b squared. So indeed, this is just 1 because all the terms in the numerator will cancel the terms in the denominator. Okay, so for the next part, we have x minus yi, and this is equal to the square root of 1 minus I over 1 plus I. We have to show that x squared plus y squared will give us 0. So now in this scenario, to simplify, right, to simplify this, all that you have to do, as we've been doing so far, is to find the conjugate of the denominator and multiply everything by it. So now the conjugate is just 1 minus I. The conjugate of this is 1 minus I. We divide by 1 minus I. So now if we multiply the numerators, we are going to get 1 minus I plus I squared. But note that I squared is just negative 1. In the denominator, 1 multiplying 1, we have positive 1. 1 multiplying negative I, we have negative I. I times 1, we have positive I. I times negative 1, we have minus I squared. Now minus I squared, as we know, minus I squared is now positive 1, remember? So this is plus 1. So if we simplify this, we get to see that this 1 will cancel out this. So we just have, in the numerator, we just have negative 2I. In the denominator, you see, this also cancels this. So we just have 2. Now, 2 will cancel out 2. So we just have the square root of... Wait, did I make any mistake right here? So let's see if we did the FOIL method right. So 1 by I. Okay, so we have 1. We had minus I. Okay, then we have 1. Then minus I. Okay, so now this is just the square root of minus I. And what is the square root of minus I? Okay, so now having this, we have